Okay, that's good.
Okay, so for the people who weren't here yesterday or just want a refresher, we talked about what an SDK is and what an op-mode is, and just basic Java things like variables, conditions, methods, and writing an autonomous op-mode outline. And we're going to go in more detail that today and actually write an autonomous program and the steps of writing an op-mode. And we'll be seeing all those today as well. So today what we're going to be doing, we're going to be talking about the Mecanum drive. So Ishan will be talking about all the different things that go with it and show diagrams and videos so you guys can have a better understanding. And then I'll be talking about encoders and how we use them and writing an autonomous program and see how they function and like the main purpose of all that. And so if we just go into Wednesday and Thursday, we talk about OpenCV and we go in a lot of detail about creating starter stack, like a starter stack detector and just like using it for this year's challenge. And we don't have at class Thursday because of Thanksgiving, but on Friday we will be implementing everything we learned with encoder movements and OpenCV and writing an autonomous program. And if we have time, we will put this in a simulator and show you guys how it should actually work. So that's what we're going to be doing for the rest of the week. So we can get started with Ishan's thing on the Mecanum drive.
All right, so Mecanum drive. So many of you have Mecanum drive robots, like drivetrains and Mecanum-based drivetrains, and I highly encourage it because you can do a lot of stuff. And specifically, I can like show you some videos that I have pulled up here that have a lot of that show like the true potential of a Mecanum drive. Let me pull up one of the videos. So this is a video of our auto from last year. And it was made obviously using a Mecanum drive. And in this lesson, we're going to talk about how to actually program that so that you can do those like complex motions in teleop and in the future auto when you get there sometime. We won't be doing that in the camp, but if you can get to that in the future, we will be setting you up for that. So yeah. So this is the auto that we did. So as you can see, you can do a lot of complex motions with the Mecanum drive. And you can go very fast, and it's very useful because you can save a lot of time using the Mecanum drive. So here we were doing like 3 stones of last year's challenge. And yeah, so as you can see, you can do those strafe movements that can actually go side to side, and you can go left to right and turn and everything. You can do everything that you, so, and then we're just going to, this is a teleop. So you can also see how a Mecanum drive can actually help you in teleop. This we will be doing in today's lesson. So this one, so in the teleop, we will be teaching you in this lesson how to code a Mecanum drive for a teleop. So you can actually do stuff like this to maximize the potential of your Mecanum drive and actually be able to go in all directions. So yeah, I'm just gonna pause that there. And then the other video that I want to show you is this is a autonomous that I created on a simulator, and I'm just gonna play it first. So yeah, it's pretty short auto, but it's very fast because it shows you the potential of a Mecanum drive again. If you want to know where we got that simulator, we might be using that actually later on in the camp if we have time, which is what we were talking about for Friday. But if you want to use this and we don't get time to use it, I'm sending the link in the chat. I highly encourage that everyone go check it out and download it. It was actually made by our team, Quantum Leap. So you can go ahead and check that out. It's a very easy setup process. You can basically create a project with the SDK. It's very similar to the FTC SDK, in fact, and you can create a project with a click of a button. So it's pretty simple, and it runs on IntelliJ, which is made by the same creators of Android Studio, and it has a cool interface and everything. So yeah, so let's get into the Mecanum drive presentation. 1 second. Oh, I need to send the link to somebody. I'm going to stop presenting really quick. Sorry. Okay, so Mecanum drive programming. So let's just start off with the Mecanum drive forces. So if you look at the Mecanum drive, you have these bearings on them, or the Mecanum wheel itself, you have bearings on them. And one thing that if you actually roll a single bearing on a table, you can actually notice that if you roll a single bearing on a table, then it's like any other wheel. It rotates if it's facing it. Well, the rotation, the movement of the bearing is perpendicular to where you're actually the way that it's oriented. So if the bearing is oriented this way and you're still thinking about a single, let me actually. So if I have a single bearing here and I'm holding it like this and it's facing this way and I start turning it, it's probably going to go this way. And that's basically how the Mecanum drive works. If I hold a bearing and it's facing this way, then it's going to go this way. Now, looking at the Mecanum wheel, we can see that if all the bearings are facing this way, then it's going to go this way. That's the general direction that the Mecanum drive wants to go. And then you can see that in this wheel too. So if the bearings are facing this way, then the general direction that the Mecanum drive wants to go is in this direction. And same with this one, the bearings are facing this way, or sorry, the rollers are facing this way. So the general direction that it wants to go is this way, and the rollers on this one are facing this way. So the general direction that it wants to go is this way. Now, we can split this up into X and Y forces. So for this one, we did a +1 and a +1 on the X-axis force. And for this wheel, we did a +1 and a -1 X-axis force, +1 Y, and then +1 and then +1 X-axis force, and then +1, -1 X-axis force. And you can notice that this one and this one are the same, and this one and this one are the same, which is interesting because without even looking at the X-axis, we still saw that this one and this one are the same forces, same direction, and then this one and this one are the same direction as well. And that's specifically builders of the Mecanum drive specifically make it like this so that it can go in these unique directions. So now let's look at how the Mecanum drive actually strafes and goes forward and all that. So if we put a positive power for all 4 wheels, then we can make the robot go forward. If we put a positive power on this wheel and a negative power on this wheel, and then a negative power on this wheel and a positive power on this wheel, then we can make a strafe. And then you can look at the other ones, and then and I'm just going to leave this slide up here for a couple seconds here. And then after that, we're going to start going into these directions and how they actually work. Okay, so now I'm just gonna go through the next part. So let's look into these directions and how they actually work. So let's start with the basic and most simple one, the going forward. So if you want to make the robot go forward, then you have to put all 4 wheels, you have to put the power to all 4 wheels as a positive power. Now, this seems self-explanatory and if you make all of them go forward, then they go forward, but there's actually some more interesting stuff going on behind it. Like I said, all 4 wheels have different forces. This wheel has a force going this way, this wheel has a force going this way, and this wheel has a force going this way, and this wheel has a force going this way. So why, when I put all 4 of them, why is it going forward? It should just go in like some weird motion. Well, the reason why is because if we put power to all 4 of them, then we can see that all the X values actually cancel out. So if you look at this one, this is a +1, and then this one is a -1 x value. So those two already cancel out. However, these two forward x, and you get a +1 on the y-axis and a +1 on the y-axis. So those do not cancel out. In fact, they add up and they make the robot go forward in a faster. It's actually faster when it's going forward because there's more force. So here you can see that there's a forward and a forward. So all these forwards add up and give it more power going forward. However, all the x-axes cancel out because this one cancels out, these two cancel out, and these two cancel out. Or you can think about it like these two cancel out and these two cancel out. Or you can think about it like both of these together cancel out both of these together. So yeah, all the x values cancel out. Now we can actually see this in a mathematical pattern. If you add up all these forces, then you get the overall force, which we saw here. So the x-axis forces will cancel out. Now this picture is wrong. I don't know why. Yeah, it's wrong. This is supposed to be -1, and this is supposed to be -1. I would just here. Let me just fix this so it's not as confusing. And also, if you ever need help, you can look at these presentations afterwards. That's part of the reason why I'm fixing it, because if anybody needs help, I don't want them to be confused by a slide that is not correct. Oh. Okay, so yeah, so with a -1, so we finally see this pattern here. If you add up all of the forces of all four wheels, then you actually get the overall force. So let's try to do that really quick. So add the first two. 1 minus 1 is 0, and then 1 plus 1 is 2, and then so now we have 0, 2, and then add these two. 1 minus 1 is 0, and then you have 2 on the y-axis, so you have 0, 2 again, and then add those two, which is 0, 4, which is the overall force, like I said. So that means that the overall force is 0, 4. So now we just found a pattern. If we add up all the forces, that equals the net force, or the net force is also called the overall force of the robot, like which direction it goes. So F1 plus F2 plus F3 plus F4 are the different wheels. So this is the first wheel, second wheel, third wheel, and fourth wheel, which is also equal to just saying x1 plus x2 plus x3 plus x4, and y1 plus y1, y2 plus y3 plus y4. So now let's look at if just two wheels were powered. So both of these wheels are positive powers, +1, +1, and +1, +1. So that just means that nothing is going to cancel out. These two wheels are not being powered, so no x value will be canceled out, and no y value will be canceled out either, because 1 plus 1 is 2 and 1 plus 1 is 2, which gives you an overall net force of 2, 2, which is exactly what we see here. Now 2, 2 is positive on the x and positive on the y, which creates a diagonal force. As we saw earlier, the 0, 4 creates a forward force. However, now 2, 2 creates a positive force on x and y, which creates a diagonal force. And specifically a 45-degree force, because both are equal. So it creates like a triangle from geometry. So now let's look at, so now we have the actual arrows, but let's draw a line so that we know, because it's not like we're always going to be setting a positive power to the wheels. We can also sometimes set a negative power to the wheels and all that. So let's draw both examples. So if I set a positive power, then it's going to be going this way, and if I set a negative power, it's going to be going this way. If I set a positive power, it's going to be going this way, and if I set a negative power, it's going to be going this way. If I set a positive power, it's going to be going this way, and then if I set a negative power, it's going to be going this way. And if I set a positive power, it's going to be going this way, and then if I set a negative power, it's going to go this way. Now, again, these two wheels are going to be the same, and then these two wheels are going to be the same direction. But sometimes I like to think of this as like an infinite line of direction. So this is the line that it would travel on, and then this is the line that the force would travel on, this is the line that the force would travel on, and this is the line that the force would travel on. But we can notice another pattern in here. So as you can see, this one was positive 1, positive 1. This is an or, it can be negative 1 or negative 1. Same here, like I said, both of these are the same, and you can see that the directions are always the same. So here we got positive 1, and wait, can I close this? No, okay. Okay, so here I got positive 1, or negative 1, negative 1. So it's the same thing as this one. However, like I said earlier, these two wheels are where it gets a little bit different. Here I have a negative 1, positive 1, and a positive 1, negative 1. And here I have a negative 1, positive 1, and a positive 1, negative 1. Which makes sense because the x-axis is the direct opposite of whatever is the x-axis here. You know, as we saw with the x and y arrows here, the y-axes are always the same across all wheels. However, the x-axis is always going to be the exact opposite of the opposing wheel. So going back to this line thing, if we know that the x-axis is always opposite, then we can make a pattern that the x-axis is the negative version of the base. So here we have negative 1, and we know that negative 1 is the negative version of this x, and we can see that here too. We have positive 1. Positive 1 is the negative version, or negative times negative 1. So that's the negative x. So you can see that this wheel and this wheel have a negative x and y. This wheel and this wheel have just an x and y. If we think that this is the base, or if we have x, y, positive x, positive y on these two, then we can say that this one is negative x, positive y, and this one is negative x, positive y. And I know that sometimes people get confused on that concept. So does anybody have any questions so far? Oh. Okay. If you have any questions, feel free to ask them, because I'm sure that somebody else has the same question as you. So yeah. Okay, let's move on then. So now that we got that pattern where negative, so these two wheels are negative x, positive y, but these two wheels are positive x, positive y. And now we can create the pattern, and let's look at the pattern now. So as I said, wheel 1 and 4 are going to be positive x and positive y, while wheel 2 and 3 are going to be negative x and positive y. So based on that, we can make all the y's positive to calculate each individual force. So if I have a force, if I have a net force, I'm trying to find the individual wheel powers based on that net force. So if all the y's are always like positive y, then we can say y, just positive y. However, like I said, wheel 1 and 4 are negative x. So I'm going to add a negative x. So for wheel 2 and 3, wheel 2 and 3 have a negative x. Wheel 1 and 4 have a positive x. So for wheel 1 and 4, I'm going to add a plus x. And then for wheel 2 and 3, I'm going to add a minus x. So now let me run through it. So if I wanted to go in overall force of forward, then then the overall force would be 0, 1, right? That means 0, x, and then positive 1, y. So let's go through the math. So 1 plus 0 is 1. So that means that this one's 1. 1 minus 0 is 1. 1 minus 0 is 1. and 1 plus 0 is 1. That means that's basically telling all 4 wheels to go in the positive 1 direction, okay? Now let's take a strafe motion. So that would be 1 on the x and then 0 on the y. So that would be 1, 0. So that would be 0 plus 1, 1, 0 minus 1, negative 1, 0 minus 1, negative 1, 0 plus 1, 1. So we got 1, negative 1, negative 1, 1. So now let's look at the sheet with all the directions. So if we go 1, negative 1, negative 1, 1, then that creates a strafe motion. And that can be seen right here. So now that we have that pattern down, let's start to convert that to code. Or let's first derive the equation. I mean, we kind of already derived it, but let's just make sure that everyone understands properly. So let me start off with the question. If the overall force of the robot is positive 1, which is a diagonal motion, then what are the individual forces? So let me just work through this. Or actually, I think I have it on next. Okay. So yeah, there's 2 ways to figure this out, right? The first method is basically to look at those arrows from before. So if we're going positive 1, that's this direction. That's this direction right here. That's this direction right here. So if I want to go this direction, then if I'm looking at all 4 arrows, this is probably not the correct direction to go because we want to go this direction, but this line is going this direction. And this one's probably not the right one to go either because we want to go this direction, but this one's going this direction, which is not even close to like where we're trying to go. However, when you look at these 2 wheels, they're both going in this direction. And this one is going in this direction too, specifically positive 1 and positive 1, which is exactly the vector that we're trying to go to. So that shows that we want to power these 2 wheels. However, do we go positive or negative? Well, I have both arrows drawn out here, so it looks like the positive one is the correct direction to go. The negative one would go this way, which is not the right way. And here also, it would probably be the positive one. So now let's look at the second method, which is more of a mathematical approach. So looking at that pattern that we saw earlier, so if I'm trying to go 1, 1, the first wheel would have to be powered. So if I do y plus x, that's 1. The first wheel would be, or y plus x is 1 plus 1. The first wheel would be powered, the first wheel would equal 2. And then y minus x, so that's 1 minus 1 is 0. So the second wheel would not be powered. Y minus x is 1 minus 1 is 0. So the third wheel will not be powered. And then the fourth wheel would be 1 plus 1, so 2. The fourth wheel would be powered, which shows us that the first and fourth wheel are going to be powered. So before we move on to rotation, I'm going to give you guys an example problem. So based on this mapping, if I want the robot to go at an overall force of, if I wanted to strafe left, what motors would I have to run and which power would I have to run them at? Like negative or positive? And you can unmute for this part or you can just type it in the chat.
If you guys want to like ask a question to like understand this better, then yeah, you can ask one as well. Like if you're confused on how you can actually solve this problem. Ishan, do you want to pull up the diagram of the robot just so they can see?
Yeah. Anybody got it yet? Oh, sorry. My bad. I keep switching to the... Nihar, just tell me if anybody types in the chat.
Yeah, I will.
So I'm guessing if you want a straight left, then you're gonna want wheels 1 and 4 to have a negative y, and wheels 2 and 3 to have a positive y. So then they would cancel out, and you'd be left with the negative x.
Okay, so you're thinking that so let's just go through it once, and then we can check if you're correct with that. So the overall vector that we want to is -1, 0. So that's this way. Let me actually draw it out on page.
Wait, Ishan, we have some in the chat as well.
Okay, let me look at them. Okay, yeah, I'll look at. I don't even know what the answer is. I have to like work through it really quick. But yeah. Let me just screenshot this and then I can draw on it. Okay. So the overall vector that we're trying to go is straight left. So that's this way. And so that is an overall vector of -1, 0. Because it's 0 on the y and -1 on the x. And then if we go through the pattern that we already determined, then that would be -1 plus. So the first wheel would be -1 plus 0. So that is correct. You said that this one would be -1. So you got that one right. -1 minus 0 is -1. So the second wheel is -1. And then the third wheel is -1 minus 0, which is. Oh wait, no, I did that wrong. Sorry, I flipped them for some reason. Oh, okay, sorry. 0 minus -1. 0. Yeah, 0 minus -1 is 1. So that one would be 1. And then 0 minus -1 is 0 plus 1 is the same as 0 plus 1. So that would be 1. And then 0 plus -1 is the same thing as 0 minus 1 is -1. So let's just go. So I'm pretty sure you got that right if I remember correctly about what you said. So let's look at the chat responses too. So we got a -1, 1, 1, -1. Perfect. Ari, good job. And then we got another person saying +1. Okay, so what? So I think you inverted them, but it was pretty close still. It was pretty close. So it's -1, 1, 1. Okay, yeah. So that one was just inverted, but it was still pretty close. So yeah. So both methods work, but for the purposes of actually plugging it into code, it would be very difficult to use the first method because it's difficult to program the robot in if statements. So one of the things that I learned over the years is that it's a lot better if you start making your code more dynamic. So if you have mathematical equations, it can start taking cases that don't actually that you can't like that are harder to solve. So like maybe I'm not always trying to go like in this direction. Maybe I'm trying to go like in this direction, you know? Maybe I'm trying to turn while doing that. So it's like that's why I'm going through the second method or this mathematical approach, because that's essentially what we're going to be plugging into the code. So now that we got that settled, I'm going to go to the adding rotation. So let's start adding some rotation into this. So to add rotation is basically created by putting opposite forces on both sides. So the left side, as you can see in this diagram, the left side actually has a positive force, and then the right side has a negative force. So that means that wheels 1, this time it's different from this is different from what we were talking about earlier, because 1 and 2 have a similarity, while 3 and 4 have a similarity. So 1 and 2 have a positive rotational force, while 3 and 4 would have a negative rotational force. So to do this, we would just add rotation to wheels 1 and 2, and then we would just subtract rotation from wheels 3 and 4. which is exactly what we're doing here. Now that we have added rotation, we have basically completed the equation that we're going to be plugging into the code. So we're not going to go into normalization yet. I just want to make sure that everyone understands what we talked about already. So does anybody have any questions?
So Ishan, like, what happens when you add rotation? What's that gonna do to your robot?
So basically when you add rotation, so what we're trying to do, our end goal here is trying to make a function that can take in x, y, and rotation, and then it's a set power function that takes in x, y, and rotation, and then it can basically make your robot go in the correct direction. And this will be very useful for like teleop and stuff where you can just plug in directly gamepad 1, gamepad 2.x, and gamepad 3.y, whatever. But yeah, it can be very useful in those kind of scenarios. It's also useful in auto, but that's what we're trying to go for. So when we plug in the rotation value, if I plug in 1.0 power, then I want to make sure that the robot rotates at 1.0 power. It just rotates infinitely, let's say. So in order to do that, if my rotation value is 1.0, then I would add 1.0 to the first wheel, add 1.0 to the second wheel, subtract 1.0 from the third wheel, subtract 1.0 from the fourth wheel, and therefore I get -1 on the first wheel, positive 1 on the first wheel, positive 2 on the second wheel, -1 on the third wheel, and -1 on the fourth wheel. And that is that creates this kind of force where the first wheel and second wheel are going forward or pushing at a forward force, while the third wheel and the fourth wheel are pushing at a backwards force. And the reason why this is only going in the y direction and not like going in a diagonal or like an x direction is because both of these x values cancel out. When you're going in the same direction on a Mecanum wheel, on 2 Mecanum wheels, then it's canceling out the x value, so you don't have to worry about them. Now, even if you're going backwards, you're still going in the same direction, so you're still canceling out the x values, which is why you don't have to worry about like any like diagonals. But that is basically what the rotation value is doing. So does everybody understand? Just ask if you have any questions, because I'm gonna move on soon, so I don't want to move on if anybody like doesn't understand. All right, let's move on then. So normalization. This one can get quite complicated, but it's pretty simple once you get it. So in order to actually maximize the speed of the motors while still maintaining the direction, we normalize these values to be between 0 and 1. So basically what we're doing is scaling down the values or scaling them up based on if they are under 1.0 or if they are over 1.0. Because you can't have values that are over 1.0. That would not be good because you can't set like 2.0 to a motor. It's not going to move. But at the same time, you can set 0.5, but there's no point in setting 0.5 when you can just set 1.0. But you still want to maintain the direction. So that would be the scale. So to really understand this concept, I'm going to go into drawing. So if I'm going forward, let's say, if I make this wheel 0.5, and this wheel 0.5, and this wheel also 0.5, and this wheel 0.5, that is going forward. It's just going at a slower, it's going at 50% power or 50% speed. Now let's go 1.0. If I go 1.0, 1.0, 1.0, 1.0, that's also going forward. It's just going a lot faster. So the similar concept could be shown for anything. Let's go strafe left. This is going to be, I think it's +1, -1, -1. Okay, yeah, so if we put 0.5, if I put 1.0, -1.0, -1.0, 1.0, that is going to strafe. It's going to strafe at maximum power. Now if I put 0.5, -0.5, -0.5, and 0.5, that is also going to strafe. It is just going to strafe, or I think that's strafing this way. Sorry, that's strafing this way, but that's also going to strafe. But since it's 0.5, it's going to strafe at 50% speed. However, I want to scale this up to 1.0. I never want to go slower. So that's when normalization comes in. So let me go to paint. So let's take an array. Oh wait, not this.
Ishan, can you explain what an array is?
Yes, I will. So let's just take a list of numbers first, before worrying about the array. So let's say that these are the values of the powers that we're setting to the motors. So 2. Okay, wait, let me actually show you an example of when it will become 2. So for example here, if you add up all the values of 8 going forward, then you end up getting a value of 4.0 as we discussed. So if you take all the values and add them together, all the y values specifically, because the x values cancel out, remember? So if you take all the y values, 1 plus 1 plus 1 plus 1, you get a value of 4. Now, this isn't the only time. You get values greater than 1.0 even when you're going through this pattern. It's not rare that you'll get a value that's like 2.0, especially when you're doing diagonal motions. So to do that, let's just say that we got 2, 1, and these are random numbers. I don't even know what direction this is going in, to be honest. If let's say that this is 2, 1.5, and 0. So I want to find the highest value. And the highest value, you guys know it's 2, but I need to tell the computer how to do that. So the first thing that I would do to find the highest value is sort. To sort, I'm just going to sort it in my head. So I would do 0.5, 1, and 2.
Ishan, can I say something quickly?
Yeah.
So in Java, there's a way to hold a list of numbers, and
Wait,
just
wait,
like
wait,
how
wait,
we,
wait,
huh?
wait.
I won't go too in depth into it. I just want to say
Yeah,
like,
I'll do it later. I'll do it later.
okay, okay.
So to find the highest value, I'm just gonna take the last component in the list because I already sorted it, so it has to be the very last one, the greatest one. All right, so now I have the highest value. So now I'm gonna go back to the first original list, okay? And then I'm just gonna divide everything by the highest value. So let's just go 2 divided by 2 is 1. Okay? 2 divided by 2 is 1. Does everybody understand? Yeah, okay. And then 1 divided by 2 is 0.5. Okay, so far the scaling is going well because I'm basically scaling everything down so it's between 0 and 1 while still maintaining that direction. Okay, 0.5 divided by 2 is 1/4. Okay? And then 0 divided by 2 is 0. So that's basically scaling. That's an example of scaling it down. Now let's scale it up. Okay, show how that works. So let's do 0.2. Let's say that we have 0.5, 0.25, 0, and let's just say 0.1. Okay, now let's sort the list. So it's 0, 0.1, 0.25, and 0.5. Okay, take the last value of the data set, which is 0.5. Okay, that's got to be the highest value because I just sorted it out. So the last value has to be the highest. Okay, and then now divide everything by that value. As you can see, now this scales it up so that's 1, because 0.5 divided by 0.5 is 1. And then 0.25 divided by 0.5 is 1/2. 0 divided by 0.5 is 0, and then 0.1 divided by 0.5 is 1/5. So as you can see, we just scaled the powers up, but we still maintain that same direction of the Mecanum wheels. So it's not going in any different direction. It's still going the same direction. It's going faster though. And that speed is exactly what we're trying to aim for right here. So that's called normalization. So this list I can put into what is called an array in Java. So let me just clear out everything really quick. So an array in Java is basically a list. In Java, you'd notate an array like this. So if I have an array of 2 or 3, 1, 0, then if I want to call an array, the index, which is the number, or the index is like the space that is in the array. So the index goes 0, 1, 2, 3. So if I want to call an index, if I can just call array, well, if this array is called array, then I can just say array 3. And then that would return my value in the third spot. So I'd find the third spot, and there you go. My value is 0. So my value here is 0. So if I make that if I assign that to some variable, then that variable would be 0. So now let's go into the code. I'm just going to explain this code. So I have public void set power, and then I'm taking in some parameters. Remember, this is going back to the methods that we learned the other day. You have the method name. You have public to show that anybody can access this from anywhere. You have void, saying that it doesn't return anything. Because here we're just setting powers. We're trying to actually make the robot move. We're not actually returning anything. And then the name of the function that we will call later is set power. And then the inputs that it's taking is x, y, and rotation. They're all doubles, so they can be decimal values. Okay. And then we're calculating the 4 motor powers using this pattern that we found. X plus y plus rotation, x minus y plus rotation, x minus y minus rotation, and x plus y minus rotation. So there you go. That's the code for it. It's pretty simple. Y minus rotation, x plus minus rotation. It's just the front left motor. This might actually be inversed. I'm not really sure, but yeah. So now we're creating an array with all the motor powers. Like I said, an array is just a list of values. So the way that you create an array is by telling the data type of the array, which here it's a double because we need decimal values. Then you're going to put the name of the array, and then you're going to put these brackets or whatever they're called. And then you're going to set that equal to, and then if you want to create the array at that time when you're actually creating it, then you put curly bracket, and then you put all the values of the array. So the absolute value of, so here we're doing the absolute value because we want a -1 to be treated the same as a 1 when we're scaling it up or down. So just don't forget to do that, because that's probably gonna, if you don't do that, then it's probably gonna break stuff. But yeah, front left motor power, and then back right motor power, back left motor power, front right motor power, and therefore. So if in this array, before I even do anything else, if I want to access the back right motor power, how would I do it? You can either say it out loud or put it in the chat. Back right motor, yeah, perfect. Yeah, that's perfect. Because again, you can't forget that the first value of the array is 0. The second value of the array would be 1, and the third would be 2, and then the fourth would be 3. That's good. Okay, so now that we got that array out of the way, we can sort. Like I said, to find the highest value, we're going to sort and then take the last value of the array once we sorted it, because obviously the last value is the highest one. So we sort the array by using Java's pre-made sorting function called arrays.sort. And then you just pass in the array name. So the array name here that we created was motor powers, and then you pass that in. Once you pass that in, it'll automatically do all the work for you and sort it. So once we're done with that, we're going to create, or we're going to have an if statement. So the reason why we're having this if statement, we're checking if the highest value is 0. Because, as you know, to do the normalization, you have to divide by the highest value. But if the highest value is 0, you're going to get a divide by 0 error. And that makes, sometimes your highest value can be 0 because, and the reason for that is just because all your values are 0. You're just not moving the robot. But when you're not moving the robot, you don't want the robot to randomly stop and disconnect and everything because you have a divide by 0 error. So that's a very important thing to check before you start dividing. So once you check that, then you could basically just take the original values before the array and then just divide them by the highest value. Because remember, we only made the array to find the highest value. We're not actually going to set the powers to the array values. We're going to set the power to the original values before the array. So you do the values before the array divided by the highest value, and that's basically going to do the normalization that I was talking about. And then once you divide them, divide equals to basically means, so divide equals to, let me just delete this. So divide equals to is like saying int val equals 5. Val divide equal to 5, and then val would be equal to 1. So this is a comment. This is not actual code, but that val divide equal to is basically, this is the same as saying val is equal to val divided by 5. So you're just saying divide myself by 5, right? And then set it equal to me. So yeah. So I'll just put this in the chat if anybody needs it for reference. So we're just dividing it by itself and then make it equal to itself. And then we're just going to set the powers to the motors. Don't worry about the motors array. That's just something that we had, we had that in our code last year, but don't worry about that. You can make these variables if you want. You know, we made them variables in our code from Monday, so we're just going to make them variables for this class.
Yeah, like if you guys remember us doing like DC motor 1 equals null, like you can just do motor1 dot set power just like that, instead of doing like a motors array where like motor 0 is equal to some other motor variable. Like that's just extra confusion at a basic level. So just, yeah, just if you guys remember us doing like the motor dot set power stuff yesterday with the time autonomous, that's pretty much how you want to do it. And you just want to pass in the variables instead of well, the variables in the set power method rather than just a variable you've defined at the top. So
yeah, so now I'm gonna actually code it for you, and we're gonna do this pretty quickly because we need to get to the next lesson. But I'm just gonna start a new Java class and call it Mecanum Drive. You can call it whatever you want. And then I'm going to extend op mode. And then I'm going to, if it's red when you click extend, when you type in extend op mode, just click alt enter, and then it'll automatically import everything for you. And then I'm just going to type in public void init, public void loop. Okay. So I'm not going to put any code in there yet because I don't have a set power method to use. So let's make the set power method. Again, like I said, for these you put at override. In fact, you don't actually, or for good practice, just do it so that you also know like what the difference between these are. But for regular methods, like for your own methods, don't put at override. This is not a method from FTC. They're not calling your method. This is going to be your own method. You can use it and you can do whatever you want with it. But this is not part of loop yet. So so like I said, this is going to be public, so anybody can use it. It's going to be void because it's not returning anything. And then the inputs that we're going to take in is x, y, and rotation. So I'm going to just take in a double x, double y, double rotation. And then I'm going to do the pattern that I was talking about. So let's go back to the pattern. This is the equation that we derived. If you remember, yeah, this one right here. So let's make a variable for the front left motor, just a value. This is not the actual motor, this is just the power. So front left power, this is not the motor, this is just the power. Because remember, the first one is front left, so that would be x plus y plus rotation. Okay. X plus y plus rotation. Double front right power is equal to, let's look at what it is. Front right would be wheel 3. Actually, I'll go in the same order as this one goes in, just for the sake of confusion and all that. So the second wheel here is going to be the back left motor. Let's do back left power. So that's x minus or y minus x plus rotation. And then let's do here and here, the third wheel was the front right motor. So I'm going to create another variable called front right power equals x, or no. Y minus x minus rotation. And then the last one that we did in that picture was back right power. And that one was equal to x plus y, or y plus x minus rotation. All right, so now we got that. Let's make our array. So again, to make the array, you'd talk about the type first. So type that I want to do is double, because I have a bunch of double values that I want to pass into their decimal values. So I'm going to do double. And then let's just call it motor powers. And then I'm going to put these 2 square brackets to indicate that I'm making an array. And then I'm going to just do equals curl, and then since I'm defining what's going to be inside the array, I'm just going to put a curly bracket. And I'm going to do same order as up there. And then front left power, front right power, back right power. There you go. I have my array now. It has all the values I need. And now let me just sort. So to do that, you do array. And Java already has a class to sort. So you just do dot sort. Nope.
Remember to do arrays with the s at the end.
Yeah. So arrays dot sort. And then you just pass in the entire array. It should just do all the work for you. Motor powers. Okay. So now that we sorted it, we can basically take the highest value by just taking the last index. Again, like I said, the first index is 0, the second index is 1, and the third index is 2, which means that the last index has to be 3. So to do that, I would put an if statement, or first I would put an if statement to check if it's 0, because I don't want to divide by 0 in the middle of my match. So that would probably mess up my game a lot more than I want to. So I would have to check for that before I do any of the dividing. So I would do divide if motor powers 3. So if the last one is equal to 0, or sorry, not equal to 0, you're saying if it's not equal to 0, then do it. If it's equal to 0, then just skip it. Okay? If it's equal to 0, just skip it. But if it is not equal to 0, then you can proceed and do the task. So I'm just gonna. So now I don't want to use these values. I want to use the. I don't want to use the. Sorry. I don't want to use the array values because I already sorted them. I mean, I guess you could, but like you already have these, and it would be a lot less confusion if you just use them. So I'm going to use the top values by doing front left power, divide equal, motor powers 3. I'm going to copy this, paste it 4 times. And here, I'm going to change it to be back left power, back right power. So there you go. I'm using all of them now. Okay. So now I scaled it down. I now did the normalization. So all I have to do now is just set the powers. So I actually did not create my DC motors yet. So let me do that. DC motor, front left.
Here, just set it to null
You don't need
instead of. Yeah, but just do it because that's what we did yesterday.
to.
It just helps understand that it's set to nothing.
Inside init, I'm gonna actually fill it up with something. Right now it's null. You don't want it to be null because when I use it in my set power method, it's gonna cause an error because it's null, and it's like you're literally telling me to do something on an empty object. So I need to fill it up with something, right? Front left equals hardware map dot get. So it tells me exactly what I need to put in there. So it looks like I need to put in a class. So that would be DC motor. And I need to put my device name, right? So my class would be DC motor. And my device name would be whatever is in your phone for hardware mapping. Let's just say that my phone has front left motor in it. It's not actually true, but let's just say that. And you also have to do this. Wait, Nihar, is this the one that we did in the camp?
Yeah, that's the correct way.
Okay.
That's how we did it in the camp yesterday. So there's actually like multiple ways you can do hardware mapping, but like this is the most intuitive way. There's
the
different
best.
hardware mapping methods you can use.
Yeah,
but
no,
yeah,
this is probably like the simplest way. I would do this, and this is what I do. So, back left, right? Front right is equal to, and then back right. Back right. Back right. Okay. Now I have to just basically set the powers to the motors. So I do front left dot set power. No, not that. Not that. Set power. Front left power. So this actually sets the powers to the motor and actually tells it to move. Back. Right. Right. Back. Right. All right, so now the set power method is done. So if I want to call that in the loop, we're going to go more into this in the next lesson in coders, but let me just give you a little preview. So if I want to call that, I would just type in set power, then I would just pass in my values. Again, the values have to be between 1.0 or 0 or negative 1.0 and 1.0. So don't put like 40. That's not going to work. So So this is going to make it go diagonal since it's a +1 and +1 on the y. And then it's not going to turn at all. If I want it to turn, I would just put 1.0 turn power. So it's going to be doing all three at the same time.
Ishan, Vignesh asked a question in the chat. Do you think you could explain?
Yeah. What type of values do you put into rotation? Okay, so for the turn, again, this is just a power. So a lot of people get confused with thinking that this is like inches or like thinking that this like actually goes to a position. No, this is just a power. So again, going back to the diagram, if I actually put in the values for the thing, so if I put in a 1.0 value for rotation, then that would make the first wheel go 1.0, first wheel go 1.0, or second wheel go 1.0, third wheel go -1.0, and fourth wheel go -1.0, which creates this negative positive force on the different sides. And that basically causes it to turn. And that can also be seen in this. If you make both of them, if both of them on this side go forward, and both of them on this side go backward, this side go backward, then that's going to cause it to turn. Did that answer the question? All right, cool. So
Okay, so yeah, looks like we're finished with Mecanum Drive. I think let's hand it over to Nikhil for encoders and what encoders are, how you can use them in your autonomous programs, potentially even teleop. So here we can.
wait, before we move on, does anybody like have any questions? You can ask them now because anyone?
And we did say that we're going to be giving the source code for this as well as the presentations and videos. So you guys will be able to look over the code for setting power to a Mecanum drivetrain. Like how Ishan kind of wrote it out. You'll be able to check that out again in the slides when we send it to tonight. So don't worry about that. If you didn't get everything copied down.
Okay, so I guess we can get started with using encoders. So basically what encoders are, they're devices that rotate and return a digital signal that can be converted into a value, which are known as ticks. Ticks will be used a lot in this program, and like we'll call that as like a separate variable. And in standard FTC DC motor, there are inbuilt encoders that we use to track the rotation of the motor. And we can see this just by plugging it into the encoder port in the motor. So if we go to the next slide, you can see in this picture how there's two cables that go into the motor. The first cable, as you can see on my cursor, that's a power cable, which basically powers the motor. That's necessary in order for the motor to run, but the encoder cable isn't. So for example, this year if you're using a shooter and you just want to spin, you won't need an encoder cable, but you'll need the power cable for it to just power. And the encoder cable, which is the other cable you see here, that is also, you also need a logic level converter if the motor itself cannot go into the expansion hub. This basically is like an adapter and just makes sure that everything is consistent throughout. And so, yeah, for Nevrest and Gobildo motors, you will need a logic level converter, but if you have a yellow jacket motor, those can go directly into the expansion hub. And these two cables are different, and they go into separate ports. So make sure you guys know that when you do it. And they obviously both go into the expansion hub. And you can have, and every motor can have its own encoder cable. So you can add that on both sides. And you can see here on this second picture that like if you look close, yeah.
Can you like talk about why we even use encoders in the first place? Like instead of just doing what we did yesterday with the time autonomous.
Okay, yeah. So basically, encoders are a more precise way of like being able to measure the distance the robot moves. So as Nihar said with time, you wouldn't want to use time because per se it's basically the power of your robot. So if the battery, we tested this before and that's why it's very inconsistent, because if you had low battery power, it would go slower in that time because all it's trying to do is just move for that amount of time. It's not moving for a certain distance. So with encoders, it'll keep on moving until it hits that amount of distance. And the way you find that distance is with the ticks. And there's this formula that I'll go into in a couple slides that'll talk about how you find that distance from the ticks. And as I said before, ticks, there's, depending on the type of motor and wheel you have, there's a certain amount of ticks that go into each motor. So you need to find that out before you program, or else it'll mess everything up. And so encoders are, I'd say that's a great place to start for new teams when they're doing autonomous, because it's much more consistent than doing time-based. And I suggest you don't do time-based at all, because there's so much variables that are involved and you'll never have a consistent result. And so you guys can see here that it does take a lot of wiring to get encoders, cables, and the motor power cables all like set up. So you want to make sure that you have a place for wire management, just like hopefully at the bottom of your robot. And you can see these blue lights on the left picture, that these are the logic level converters. So basically a way you can tell if it's working is that if it lights up blue, so you can just make sure you have the signals. And here on the right, you can see that these are the motor ports, and you can't really see it, but the encoder cables would also be right there next to it. And so this presentation will be linked, and you guys just want to watch this video about the motor encoders, you can just click that. So here's the encoder formula that we're going to be talking about today. So basically, we just start with the ticks per revolution variable. So this actually depends on the type of motor you have. So if you have a generic Tetrix motor, this is the amount of ticks per revolution. But some other motors that we use, like the Everest 20-to-1, that was like 1600 or something. So you can just search it up, and you'll be able to see it very easily. So make sure you guys just do that and don't just use the default that they give, or else you'll have very different and skewed results. So if we go on to the next one, the drive gear reduction, this is depending on how you build the robot. So if there's no gear, so if your motor axle connected straight to the wheel, that would be 1, because it's not geared up or geared down at all. But if you do gear it up, which is basically having that axle on a gear and having another gear attached to it with this, which is connected to the actual axle of the wheel, that would mean it's geared up. And you just want to make sure that your builders will tell you what the gear reduction is, so you can accurately put that into the formula, because this formula will be used all throughout the program and like the methods to get the robot to move. On this wheel diameter, so this is basically the diameter of your wheel, because it depends. Like if you have a very tiny wheel, the wheel diameter will be less, so it'll take less ticks per revolution to come through. So using this, you'll be able to, the formula will be able to tell how much like the diameter of the robot, the diameter of the wheel is. And then here, the counts per inch. So this is basically the equation it uses with all these variables, and it'll give you the counts per inch. So you see the ticks per revolution, and then the gear reduction. So if you multiply those and then divide it by the wheel and diameters times pi. So if you just this is all this will be in the GitHub source code as well. So you guys can just copy paste this formula and just change the numbers. And then so that'll just give you, yeah.
But can I say something? So just so you guys understand, like ticks per revolution, like each motor has a different amount of ticks per revolution, and based on that, so 537.6, you can do a conversion, and that's what this counts per inch means. It basically, the counts per inch variable just means that how many ticks am I traveling for a certain amount of inches. So and that also is based on your wheel diameter and circumference. So that's what that calculation is doing. So all those variables are just used to figure out how many ticks you want to travel for how many inches you want to go.
Okay, so that's basically what the encoder formula is. We'll use that again later today. So if we move on to the next slide. So this is kind of how we set up the program using the if statements. So basically, if you guys don't, we used if statements on yesterday, but basically it gives it's a conditional. So if this is using last year's code, if the skystone position was left, it would do this code, but if it was middle, it would do this set of code, and if it was neither, it'd have to be right, so it does this. So that's usually how you do encoder methods and do basically anything when you have different variables. So usually using webcam, if you have 0 rings, it'll do one set of code, or 1, it'll do something else. So you just want to make sure you have this, or else you're just going to be doing like the same set of codes, even if you have a different objective, depending on the amount of rings you put. So this is basically like a zoomed in version of how you call your method and the parameters you put inside of it. So don't disregard the 30. We're actually taking that out because that's just the timeouts, and it's always going to be 30 because autonomous is 30 seconds. But if we start from the first one, the 0.4 and like the first one, that's the speed. So that's the speed you put the robot. So if you want it to be faster, you put it as 1, and if you want it to be slower, you'd make it closer to 0. And the next two is the distance that the left wheel travels and then the right wheel travels. So like the 24 here, it'll travel 24 inches forward, and then the right set of wheels will travel 24 inches backwards, which will make it turn. So that's sort of one way you can do a turn. And if you don't like doing that, you can just create another method, it'll do it itself. And here, because both of them are the same way, they'll both move 7 inches forward. And so you can see the strafe drive, which is basically, as Ishan talked about today, which is like Mecanum drive. It's talking about how the robot can strafe left and right. And the way, and we'll make this method as well, but you just want to have opposites, because the only way that they can strafe is that if the diagonal wheels are moving opposite directions, and you have to make sure the correct one's negative in order for it to move the right way. So this is something you guys will be able to see this very clearly. But this is like the encoder method that we're gonna program today. So if you look on the right, you can see how it says the run using encoders, stop and reset encoders. There's different types of these, and we're gonna be using almost all of them, because the way we do it is that we first have to call the encoders to run, because they're not like in the program. You have to like first like call them to work, which we're gonna be doing in the init, So we're going to be doing all of those. And then you just want to make sure that you have it for every single motor, because if you forget one, it's going to cause an error. So there's going to be a lot of copy pasting to repeat it. So if you guys want to follow along, just make sure you guys do that. And this is actually not in op mode. There's something called linear op mode, which I won't get too much into. But it's basically this. It's just a different format of how you program, but it's very similar to op mode. But there's just some minor changes that we're not going to talk about because it's not necessary for now. And so this is the strafe method. This is the thing that really changes. So if you see on the bottom, you see how it says the FL and the BL are negative. That's because you want those to be flipped, as I said before, with the diagonals, because you want the diagonals to be the same. So if once you want that, you're going to have to edit the regular method, the regular encoder drive method, so it can change it. So instead of having the left wheels both go forward, you'd have the one set of diagonals go forward. And that's what this negative does. So if we want to get into the programming part of it, wait, do you guys have any questions about the slideshow, first of all?
So we didn't really go into the actual like definition of the encoder method, so don't be worried about that right now, because Nikhil's gonna like live walk through exactly how like you actually create the method to make your robot move a distance. This was just kind of like a quick overview of how you can actually execute the method and like how encoders work.
Yeah, so if no one has any questions, I'll present my Android Studio real quick. So let me get that.
And you guys can follow along with this as well. I just want to ask, so everybody that's still in this call, do you guys all have Android Studio installed properly? If not, I'll join a help session with you guys. And just type in the chat if you don't have it installed.
Let me make it so you guys can see it better.
Okay, I'm assuming everybody has. Okay, unable to access it as of now. So do you want to join a help call with me right now and get it installed together, or is that something you want to do later?
Okay, so I guess if we don't have an answer to that, I guess we'll get started. So can you guys see my Android Studio?
Yeah.
Okay, so we'll start by making a new Java class. We'll just name this testing encoders. Java. Okay, so can someone walk me through what the first thing you want to do when you first start creating a program is?
Extends up OP mode.
Extend off mode? Yes, that is what we're going to be doing. Does anyone know what? There's multiple things you can do first. What does anyone know? Anyone want to tell me what you want to do first before we start programming, like to get it all set up?
Well, since this is with Encoders, it's probably going to be an autonomous, so add autonomous.
Yeah, and autonomous annotation. Then you can also, what you want to do is just like create a name. So I would suggest naming it the same thing as you name the class, testing encoders. And you guys, obviously, we need to create the two like methods. So the public void in it. Like, I would suggest just like having them both there first before you start programming anything. So what we're gonna do first is that we need to hardware map the 4 motors. So what I'm gonna be doing, well, not hardware map, sorry, first to initialize them. So the way I name them usually, and like what our team has done, is that we just name them FR, FL, BR, BL. So like the front right, front left, back right. So like if you guys want to do it the way you usually do it, that's okay. But this is how we're going to be doing it for today. So we have to initialize all 4 of them. So if someone's following along and I'm going a little too fast, just let me know. So FR, FL, BR, BL. So now we'll get to like hardware mapping everything. Actually, no, before we hardware map, we want to get the formula. So I don't want to type the whole formula. Yeah.
So you want to like declare all of your variables like we mentioned before, and these variables will be used to calculate the amount of ticks for a certain amount of inches. So like you can actually not use this formula, and you can actually just plug in that ticks that you want to go. Like you could do like 2,000 ticks or something, but that wouldn't like you don't. That's not like a nice number that you'll be able to figure out the actual distance on your field. So that's why we do a conversion to like an inches conversion to ticks, so it knows.
Yeah, and if you guys are following along, I just put it like this formula into the Google
Nico,
Meet chat.
don't put it in init. Put it after the
Yeah,
motor.
outside.
Yeah, put it after the motors variables that you've. Yeah. So the reason why we do this is so we can have access to these variables in both of our methods, init and loop. Don't worry about the final keyword in front of the variable. Just look at
I'll
the double.
talk about it.
Yeah.
Yeah, so basically, like you guys know what a double is. It's basically just like a number with decimals. And like what a final means is that like I tried using it a different way, but like it gave an error. So it just basically means that the value of this variable won't change. And like it's not because these are going to be steady numbers, because once you plug them in once, that you're not going to change them. So like I'm just going to go on the internet and search like if we use a Nevers 20:1, what the picture revolutions are going to be. So like give me 1 second. Like you guys should do
let me
these.
just ask a question to you guys. Like, what motors are you guys mostly using for your drivetrains? Like, are you using Go Builda Yellow Jackets, Neverest motors?
We personally got Yellow Jackets.
Okay, yeah, we actually use Go Builda Yellow Jacket 19.2s as well, and we gear them down to get a faster drivetrain. But yeah, so you want to search up which motor you're using. So Okay, yeah. So 13.7 is like maybe if you're using like the Strafer kit or something, right? You can just look up the go build a motor, and then there's gonna be some specifications on the website, and it'll tell you how many ticks per revolution you have, and that could be, I think how they say it, it's like cycles per revolution. I think I'm not super sure what the actual term they have is on the website, but it's the same thing. So just depending on your motor, there'll be a different tick count per cycle.
Yeah, so
Per
for the I
revolution
just
of the
searched up for the
shaft.
Neverest 20 to 1 ticks per revolution, and it gave me 134.4, so it's very easy to find. And the gear reduction we did last year was 2, and like the wheel diameter, we'll keep this at 4 because that's kind of what we done. It doesn't really matter. Make sure it's the same number. And if you guys
Yeah,
ever
like
rebuilt or anything, just make sure you guys change it here so it'll still be consistent to what you guys done.
yeah, and like if you're gonna be using Mecanum wheels, I'm like 95% sure it'll be 4 inches. If you're using the smaller like Rev ones, like Rev has Mecanum wheels that are, I think they're like 2 point something inches or maybe 3 point something. They're the smaller ones. You'll just have a different wheel diameter for inches. So just
Yeah,
note that.
so basically that's kind of like the formula. So you just want to make sure you have that in before you do anything else, and make sure you update it if it needs to be. So now we'll start hardware mapping our 4 motors that we visualized. So like yeah, the hardware map, get, and you need to put the class name as well, and then FL. So we do this 4 times. Okay, so let me just finish that. So next what we have to do is that now that we're going to be using encoders, is that we actually need to set the encoders and then make sure that the program knows we're going to be using those and not using anything else like time. So what we have to do is that, I'll start with the FL, is that we need to set like the encoders and basically make sure that there's nothing on it, no data that'll skewer like what you're going to be doing next. So basically what we do is that we'd call the DC motor and then we just stop and reset. Okay, so basically how we do it, the set mode. Oh, one second. A DC motor dot run mode, and then we're gonna be using this set mode dot DC motor dot run mode for like almost everything encoder wise. And then now what we need to do is, because we are gonna be stopping and resetting the encoder just in case our previous program might have anything tracked. This is just something good you want to do. We do stop and reset encoder.
Nikhil,
And we
can
want
you
to
put
do
a comment above this just to
yeah,
make sure that you know what you're doing?
comment below. Previously on the encoder.
Yeah, and it basically just says that your current ticks traveled is 0. So if you think about it, after every method that you call, like drive this distance, you want to reset it back to 0. So you can just say drive this ticks, and you'll see more of that in the method when we actually write it.
And the reason we put this in the initialization is because we want this to do this every single time you run the program. So when you click init, this will happen. And so another thing that you do when every time you have a program that'll move the robot, even in Teleup, is usually if you have a basic drivetrain where 2 motors are facing the opposite direction compared to another, you need to set the direction to reverse of 2 motors that are in the same on the right side. So then basically if you just do everything positive, the 2 on the right will flip, so it'll all go the same direction. If you guys it's kind of hard to explain without showing the picture, but if you guys go back to the picture, I don't want to change my screen, but if you guys go back to the picture which I showed with the the logic levelers, you can see how motors are facing the opposite direction, and then doing the set reverse will basically just offset it, so everything's technically facing the same direction in the program. So that's something you'd want to do not just in autonomous, but also in every like teleop or anything you're doing with the robot. And you'd only do this for the drivetrain motors. You wouldn't do this for anything else unless you need to. And I'm going to choose doing it to the right side, so you do it for FR and BR, nothing else. Okay. Okay, so that's all we have to put in the init. So now, before we start actually calling the method, we'd have to create it first. So what we're going to be doing inside, actually this isn't in the loop as well, because the only thing we actually put in the loop is we call the method and what it's going to run. So what we're
Yeah,
going
and
to do is,
here, one rule about Java is that you're not allowed to define methods in other methods that you're defining. Like, so if you look at this public void loop, like you're technically defining loop. And Nico, you forgot to put the at override. Remember to
oh
put
yeah,
that?
I put it for the first one.
Yeah. So you're not allowed to do another public void method and then the parentheses. Like you can't define a method in another method that you're defining. That's just something to remember. That's why we do it outside of. So we're still doing it in the same class, just not in a method.
Yeah, so now we're going to be creating the encoder drive method. So as every method, most methods basically start with is the public void. And we're going to name this encoder drive because that's just like a name you have. And you want to name your method something that'll actually relate to what the function of it is. So now we just create the parameters. So as I said before, the first one is like the speed or power. And then I'm going to name this left inches and right inches. And we created these here, and the reason we have these doubles is because we can only have these, especially for speed, it's 0 and 1, and so it's most likely going to be a decimal. So if we have an integer, it's going to throw an error and it's not going to work. And for the double, for the right inches, you might need a decimal. That's always a good thing to have. So now we'll start by creating the method itself. So the first thing you want to do is we're going to create a front target. So basically what this does, so basically what's like there's a new left front target, new right front target, is that we use this later on into our method to like actually set the target position. So like that target is basically the distance we want to go. So like that it'll calculate the difference between it and move that distance. So we have to do this 4 times as well because there's 4 different motors. So what I usually call it is like left front and then target. And you always want to have to equal something, and we're gonna have it equal to 0 now, but it'll calculate what it's actually gonna be equal to later in the program. New right, oops. Target left back target equal 0. Right target equal 0. Okay, so once we have that, what we're going to be doing is, as I said before, with this new, like these 4 different variables we just created, we're going to calculate the positions of them so they'll be able to tell the difference. So what we're going to be doing first is with the new left front target, it's going to equal. So what we have here is like the current position. So let me just type it out real quick. So current position. And then that it's going to also add, one second. Okay, so basically, let me just type it all out and explain what it does. Okay, so
Technically, you don't need to do the double left inches and right inches. You can just do int left inches, right inches. So you don't have to convert it to inches, which is what you're doing right there. But that's fine.
where?
Like, you know why you have that int in parentheses? You're converting it to inches right there.
Okay.
So you don't need that really. But I mean, you can just keep that. But just know that you don't want to be passing in your left and right inches as. I mean, actually, honestly, yeah, just keep it how it is because it's gonna round to an int value.
Yeah, so
it's fine,
basically what this does is that you guys know what the counts per inches because that's how we calculated it in the formula. and the left inches is what you put in when you actually call the method, and then you put that as a parameter. So then those will multiply, and those will add it to the get current position. So that's basically the position it's at, which is it's 0. So this is because every time you, at least for now, because this is the first time we're going to be doing it, it's going to be 0 plus the distance you actually run. So we're going to be doing this 4 times. And as you guys expect, for the motors that are on the right, we would do right inches, of course. And the reason we do this is because we wanted to make sure that the left inches are actually the same. That's why we don't have 4 different variables here. And I also have to change this as well. Okay, right front.
And I don't think Nikhil went over this, but fl.get current position or an fr.get current position, that method returns the current ticks that have been traveled so far. Right?
Yeah.
So your position, technically it should just be 0, but yeah.
And you want to
So
make sure. Okay.
Well, actually that won't be 0. So the first time you do it, it'll be 0. But then after you've traveled your ticks, the current position will be whatever the ticks you've traveled. And you're just adding on to it the ticks that you want to go.
Yeah, because you're gonna add on to it, so it doesn't really matter what it's at because you're just gonna add on and then go from there. Okay, so yeah, you basically just want to make sure. Yeah, you want to. Oh, I gotta change this too. You want to make sure that the left inches go with the left motors and the right inches go with the right motor. And so now we're gonna go back to the same thing that we did before, as I mentioned up here, with the setting the modes. So we're gonna copy this and put it here, but actually instead of having it stop and reset encoder, we're gonna have it so it's run to position. Yeah.
And so basically, here, just write that. Let me explain run to position. So basically, run to position is a run mode where it allows you to say fl dot you can just say fl run to this position, and that position will be in ticks. So similarly to get current position will be maybe it'll be 5,000 ticks after some point. Then say your conversion that you're adding on, so your the inches that you want to go converts to 500 inches, or I mean 500 ticks. So your final target will be 5,500, and you've already gone 5,000, so you're just adding 500 ticks onto that. And then you can say fl, I want to set my target position at 5,500, and it'll just go that extra 500. So
Yeah, and
that's how run to position works.
And something we actually forgot to do before is that once we got this thing, we actually have to set that as a target, because right now this just carries the number. So right now we actually have to use it, and we call something called set target position, and then we use that as a parameter so it'll know how far it has to move. So something we have to do is that set target position, and then we would just put in new for FR, it would be the new right. Actually, I'm gonna do FL so they're all in the same order. So it's
And
new.
Nikhil, after this, can you please comment the blocks of code, just explaining what they are?
Okay.
Any questions so far, guys? If you want us to explain a little more on what the different run modes are or how encoders work, just please let us know.
And the L. So yeah, it's kind of tedious when you have to do all 4. Okay, so I'll just kind of go through some of the stuff we've done already. So this basically, yeah, sets it to 0, and what this does is that this offsets the two that are facing the opposite direction. Okay, so yeah, you guys know what the public void loop is. This is basically where you call all the methods and it'll run everything. So the new left front target, this creates the variables. Yeah, you guys know that, yeah, these are the parameters that are in it. What this does basically, as I said before, it calculates the position, it calculates the distance it has to move from like left inches and the right inches that you put into your formula. I mean, into the method when you call it. And this, then set target position, this actually like sets the target of the position, so it'll make it move, like being ready for it to move. Okay, and yeah, this run to position, as Nihar kind of said, is that this basically just gets like this doesn't use the encoders. This basically just has the like it just basically has the robot, so like it can like go to that position.
Yeah, like basically, so once you've set that target position, it's gonna say that like you're setting the mode, so whatever power you set, it'll stop after you've reached that target position. So like I was explaining before, if your target position, so if your current position was 5,000 ticks, your new current position of that motor is going to be 5,500. That's going to be, and then you're setting that target position using the fl.set target position, whatever method or like whatever motor and then target position method, like whatever you're going to do there. That's going to set the target position. Then you're going to change the mode to run to position, so then it knows to actually stop at that target position. And then you set power, and then it'll just stop by itself once it's reached that power.
Yeah, and so as he just said, we actually need to set the power. So this math.abs is actually something that like converts the speed into the power. So you want to, the reason we call it speed is because the speed that we get from the encoder, so what you put on it, is 0.4. It'll like convert that into the power that the motors will run. So without this,
Math.abs just means it's just a function to take the absolute value. That's what math.abs. It's just another method. It's a math method. So it'll just return it back into a well, actually, you don't even need that math.abs, to be honest. Just
I mean,
keep it
you can
positive.
technically just plug it in straight into it, but it's just something that we've done.
Well, yeah. Well, your power is gonna be between 0 and or -1 and 1.
Well, you can just do technically, like if you look here, you can just set power and then put like the speed. I think, yeah.
Yeah, you can, but like, yeah. Let's just keep this math.abs to. Yeah, that's fine. Because if your target position is negative, it'll know that. For example, like if you're gonna do a turning motion, like a tank turn, and one side is gonna be negative and one side is gonna be positive, then your target position will be negative because your ticks will be also negative.
Yeah, that's true. So next, what we have to do, so this basically, wait, let me just. So this gets, yeah, absolutely. Okay, so now this basically has it ran, just ran the whole program. So like, cause it runs. So basically, if I go through again, this like instantiates the variable. This calculates all the math, which will have all the positions, so you'll know how far it has to run to. This gets the target position, so it like has, so it gets the robot ready to move. This actually moves the robot, and then this like gets the speed, so you'll know how fast you have to go, and like that's how the motors know. So what you have to do now is that once it happens, we need to stop all motion. So we do fr.set power, and we make it 0 so that nothing moves. We do that. We make it fl. It doesn't matter here. So then do that for all four. FL, BR, BL. So yeah, all four set to 0. And now what we want to do is that because we've never actually turned this off, it's still trying to calculate the next run to position. So what we're going to do next is that we're actually going to turn off the run to position, and this uses two different run mode, like two different types of the run mode. So what we're going to have to do first is that we need to like show that it's using run using encoders. So we're going to, let me just copy it from here. Let me just make sure it's, all right. So now instead of doing run to position or stop and reset encoders, we're actually going to have it say run using encoders. So like, here, let me finish doing it first. Run using. And this is because right now, like when does the set, what is it? Yeah, the run to position, like they might not think that's using the encoders. And like once we actually call this run using encoders, it'll have like basically the encoders pulled up. And the next thing that we're going to be doing is like doing stop and reset encoders. And this is also something that we did in the initialization. But we want to do this at the end of every method because we're going to be calling encoder drive multiple times because you want to move forwards and backwards. If you don't use the stop and reset encoders, it'll just keep on adding that together. So that's like why stop and reset encoders is very important to use. Let me just get it for all four. This resets all the data for the encoders. Okay, so it's just something you can also do, which I wouldn't really suggest, but if you're just trying to test things out, is add a sleep at the end of the method. So after every movement, it'll like stop for like just a short amount of time, so you can really debug if anything's happening. But I'm not going to keep this in the program because that's not something you would need very often. It's only when testing. And I don't think we've gone over sleep, but sleep basically just, it's kind of like a sleep. So it just like stops what's
Well,
happening.
actually, we can't do
When it,
sleep in regular op mode. Remember?
oh, you can't,
So
non-regular
no.
mode?
So we're gonna do the elapsed time thing.
Elapsed time,
So
okay.
so let's not go over that right now because I mean,
Alright.
yeah, it's not really a point.
Yeah, but like if you like later on, if you guys need something like later on the season, there's always something out there called sleep or elapsed time, which will stop like the time. So you just look into that if you need it, and it's pretty helpful when debugging stuff. It's like splitting up each motion very like into separate parts, so you'll know if there's something wrong with like an actual build thing or one of your program movements are not correct. So that's a good way to debug. Is just like break everything down, and so that actually looks like there's no errors. That is the encoder derived method. So that's basically how you get it to move forward and backwards. And another way that you can get the strafe to work that Ishan didn't talk about, but something that we did last year because we had this method, is that if we copy this and create another one, but instead of naming it encoder drive, we name it strafe. As I mentioned in the slideshow, that if we go to the, if we go to, let me, one second. Yeah, the set target position. I want to make sure I put it right on the slideshow. The set target position. You want to make sure. Yeah, you want to make sure that the diagonals actually go the same direction. And because the new left front target, these are actually to calculate the distance that's going to be moving. You're going to want to make the opposite. We're going to want to make the negate the opposites. So basically, what you're going to be doing is just making them so they go opposite. That's why you don't do it for FR and like BR. You do them for the diagonals, so the diagonals are basically connected to each other. So that's kind of really all you have to do to make it strafe. So now that we've created both of these methods, then in the strafe drive, yes. Basically what you're going to be doing, you can't just run this and expect something to happen. And you see that this loop is empty. That's because because in this loop, that's where you call your method and the program actually runs. So if we talk about this year's challenge, where you have to find out if the height of a stack is 0, 1, or 4. So you, in the end, use some sort of webcam detection or phone detection to figure that out. And that's also something you're going to have to put in the program so it can like you initialize it there and detect it. But that's something we're not going to go into. So just to like you guys know what we're going to be doing. I'm going to
Well,
create
actually,
another variable.
so webcam is gonna be, or detection is gonna be tomorrow. So you will
Yeah.
actually learn how to do it. But
Yeah, and that's
for
actually, if you
the
guys look
sake
on
of
Friday's overview, you'll see how we implement both of them together. But for today's purpose, we're not going to create.
just think of a detection thing going on in this program, and so
So
right
I
now
just,
Nikhil's gonna create a variable right here called stack height, and he's just gonna initialize it to 0. And during init, the stack height variable will actually change, and it'll be updated using the detector. So the detector will, the value will change if it's 0, 1, or 4. So
yeah, and so basically, as I said before, the very easy way to do it is with doing like an if or if else statement. So I'm going to do this. So if the stack height equals 0. So what this means, if you do 1 equals, that's basically assigning that number or value to the variable, and that's not what we want here. We want to see if they're the same thing. So that's basically what the equals is for. So if the stack height is 0, which it is at the moment because it hasn't been updated by anything, then we would do something. And then if it, wait, is that how, yeah, wait, I'm on
no. You put an else after the last curly brace. Else if.
else it, not if else, sorry.
Else
Else
if
if,
parentheses, yeah. And then
yeah, stack height. Then because it's 0, 1, or 4, we're going to do if equals to 1 with the updates to 1. And then we would do else. But the else, because you, I'm not sorry, not you do my pipeline in the way, but else, because if it's not 0 or 1, you know it's 4, so you don't really need to create anything to do the equals 4. And so now that we have the 3 different statements, the conditionals, which will tell you if it's 0, 1, or 4, what we're going to do is that we're going to actually use the methods we created. So encoder drives. So now this is where you put in your 3 arguments. So this actually isn't going to do anything, obviously. So I'm going to say the speed is going to be 0.5, and we're going to go 20 inches forward. It's 20, 20. And that's sort of how you do it. And that's like the basis to like everything you want to do. If you want to go straight, or if you want to turn, I can do another thing here, encoder drive. And we don't want to turn fast because we want to make sure it's accurate. We'll go 30, and then negative 30. And I suggest when it comes to turning, you don't use an encoder drive because you won't really know when it's a 90-degree turn. You want to create your own method and calculate that yourself with the angles. But for now, we'll just use the encoder drive. And if you don't know how to create the next method by yourself, you can just use this. And if you go to strafe drive, speed itself, we'll make this 1. Left inches, we'd have at 10, negative 10. And you want to make sure that they're opposite as well. Like, so no matter what it is for strafe, or else if it's the same, it'll go forward and backwards. So when you do this, you have to test with, depending on how your robot's built, is that if the right inches is negative, will it go left, will it strafe to the left or strafe to the right? So that's kind of that's how you do it. And like, if you want to create a servo, like, because if you're gonna use this and like create your whole program with it, you'd have to use servos and other motors as well.
yeah, let's not go into servos right now, but like just to clear everything up, like this strafe method doesn't, it's not the same way that Ishan taught you guys how to do the set power method, because here what we're doing is we're just hard coding the negatives for the motors, and we're not passing in an X power, Y power, or rotation power. This is literally just going to be a left and right strafe. And I recommend you stick to left and right strafes in autonomous with so far, just because if you start doing fancy things in autonomous with purely encoders, things start getting really inaccurate, and you can get pretty far with straight lines, point turns, that type of stuff. And I actually personally recommend you do that over anything more advanced for this season, just because it's not worth it to, spend the extra time to do something more fancy rather than maybe working on your teleop or something. So
Yeah, I completely agree. Left strafe and right strafe do go a long way, and you're able. Strafing is very important and makes programming
And
comments very easy as well.
and what we mean by left strafe and right strafe is like moving at a like exactly to the left direction and to the right direction, not
Wait,
like
you
moving
showed
at
a
like a
video of a strafe, right?
no, he just showed his auto. So their auto, like they moved at like maybe instead of moving perfectly like 90 degrees or perfectly, so if you're at like a 0 degrees position, right? If you think of that as your heading, instead of moving 180, maybe moving at like a 45. So that'd be like a diagonal. So like you're not able to do that with the strafe drive method currently, but you can actually create that on your own if you'd like to, but I personally don't recommend it with this encoder method right here, or not method, this encoder strategy.
Yeah, so I commented on most of it, and this is gonna be in our GitHub source code if I post like today or tomorrow. And you guys will be able to you have this program and have the comments and be able to like recall from the video of what we talked about if you don't have any, if you don't understand. Do you guys have any questions about any of this? Like, can we go over something?
Yeah, do you guys have any questions about this encoder stuff? Maybe if you want us to clarify the method a little more, like how the method works. Let me just ask a question to you guys. Like, so far, like how have you been programming your autonomous? Or maybe in the past, how have you done it? For maybe if you use blocks.
We're a pretty new team. This is our second year. And last year, because of all the COVID and stuff, we were kind of lucky because our autonomous was actually based on time. Basically, we just calculated the amount, how much space we could cover in a certain amount of time. But as you said, that led to certain inaccuracies, depending on battery, on our battery life, and all that kind of stuff. So
Yeah,
this is definitely gonna do so much better, especially since we upgraded our drivetrain too since last year.
yeah, that's
Yeah,
I
yeah,
good
definitely.
to hear. And I suggest like never do time honestly, unless you're just trying to test if motors work and like to shoot power, like just to shoot. But I would never like suggest unless you don't have any other way to use encoders, not to do in time, not to do time because very very inconsistent.
All right, so it's 3:30, so if you need to leave, you can. And tomorrow, we're gonna we're gonna talk about OpenCV, but before we do that, we actually forgot to talk about teleops. So we're gonna first talk about that and then move into OpenCV. It shouldn't take too long. So if you are looking forward to a teleop lesson and a camera lesson, so you should come tomorrow. It's gonna be pretty fun. So yeah.
And make sure you guys check the virtual hub like a couple hours from now because we will update it with everything and we'll probably send an email with what we've done today and yesterday and probably have the source code in there as well.
Yeah, make sure you get all the source code from all these lessons. You probably already you probably already did that like during the lesson, but make sure you get that because we're gonna be using that tomorrow. And then Nihar, do you have anything else to add?
Not really. So for tomorrow, for the camera stuff, if it's not going to be building off of this encoder stuff that we learned today, but it will build off of the knowledge that we learned about Java and op modes. So I would recommend you guys just brush up on that again, just so you guys have a good understanding and you'll be able to, get started working tomorrow.
And if you have any questions about accessing anything or just anything we talked about, and if you have to like leave early and you're just watching this recording, just email us and we'll be happy to like maybe get on a call with you or just email you with what we think is correct. So just email us even if you're watching this recording. We'll be happy to help you either way.
Cool. Thanks a lot.